Hi guys, and welcome to AP Calculus AB Transcendental Functions. Today we're going to be talking about how do we integrate complex rational functions. By the end of today's lesson, you should be able to integrate complex rational functions. We're in section 5.7 in the book, if you want to follow along in the book. And once again, everyone should be working on the transcendental functions homework packet. There's several rational expressions that you need to be able to identify upon inspection. You need to be able to commit the following three rules to memory. The integral of du over radical a squared minus u squared is arcsine of u over a plus c. The antiderivative of du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. And the antiderivative of du over u radical u squared minus a squared is 1 over a arcsecant of the absolute value of u over a plus c. Okay, so let's give this a try. Why don't you pause your computer right now and then see if you could solve this. If you've solved this correctly, we're going to let a equal 3, which 3 squared of course is 9. U in this case is just x, and so it's 3 squared minus x squared, which is arcsine of x over 3 plus c. If you got that, good job. See if you could solve the next problem on your own. In this case, we're going to let u equal x squared minus 5, and that whole quantity is getting squared. So then that means that du is going to be 2x dx. We have a 3x dx. We're going to go ahead and take the 3 and factor it out. We're going to multiply by 2, but if you multiply by 2, we've changed our problem. So we're going to have to change it back by dividing by 2. A in this case is 2, and so 2 squared is of course 4. Once we set up our u substitution, we're going to say 3 over 2 antiderivative of 2x dx over 4 plus the quantity of x squared minus 5 squared, which is 3 over 2 antiderivative of du, because 2x dx is du, over 2 squared plus u squared. And this, of course, is arctangent. So this is going to become 3 halves times 1 over a, so 1 over 2, arctangent of u over 2, u over a, plus c. And then we just have to substitute our u back in, and we get 3/4 arctangent x squared minus 5 over 2 plus c. If you got that, excellent job. See if you could do the next problem on your own. In this case, we're going to let u equal sine of x. If u equals sine of x, then du is cosine of x dx, which is very convenient since we have a cosine of x dx in the numerator. We could then substitute sine of x with u. We get cosine of x dx, which is du, over sine of x, which is u, radical sine squared, u squared, minus a squared, which in this case a is 5, and 5 squared, of course, is 25. So we could use our u substitution, and this becomes the antiderivative of du over u radical u squared minus 5 squared. And if you've memorized your rules, you should know that this is arcsecant. So we get 1 over a, which is 5, so 1 over 5 arcsecant of the absolute value of u over a, which was once again 5, plus c. If we substitute u back in, our sign, we get 1/5 arcsecant absolute value of sine of x all over 5 plus c. If you're able to get that, excellent work. Let's try another one. In this case, this poses some problems because it doesn't really match any of our rules, but we can make it match. And what we're going to use is our good old friend completing the square. If we complete the square here, you should know that 20 can be rewritten as 16 plus 4. The reason we want to get 4 is because our middle term 4x, right here, this middle term 4x, we know half of that squared is going to be 4. So we know if we want to complete this square, we need a 4. So we're going to go ahead and subtract 4 from this, which will leave us with 16. This right here is a complete square. That being said, If we complete that square, we're going to end up with dx over 4 squared, because 16, of course, is 4 squared, which is going to be our a, plus x squared plus 4x plus 4 is a completed square, and it is x plus 2 squared. That follows our form of arctangent. We're going to let u equal x plus 2, which of course means that du is dx. So the numerator becomes du all over 4 squared plus u squared. And so once again, this is arctangent. So we get 1 over a, 1 over 4, arctangent of u over a, u over 4, plus c. We just have to substitute our u back in, and if you do that, you get 1/4 arctangent of x plus 2 all over 4 plus c. Let's try another one. See if you could do this one on your own. So once again, we're going to want to try to complete the square. So we're going to look at this, and we're going to look at the first part, which is x squared plus 8x. To complete this square, we need half of the 8, which is 4, and we're going to square it, so we need 16. So we have 23. We know 23 plus 7 is going to give us 16. Now, this, of course, x squared plus 8x plus 16 is now a perfect square, and that's going to give us x plus 4 squared. The problem is we have the 7. So what do we do with the 7? Because it needs to be, if we follow our arctangent rule, it needs to be a squared plus u squared. So this right here is going to give us our u squared, but what about our a squared? In order to get that, well, it's really simple. We just take our 7 and we square root it and then square it. If you square root and square it, it goes back to 7. And so that gives us our a squared. So a in this case is radical 7. So once again, we're going to use our u substitution. We're going to let u equal x plus 4. du is dx. Now that du equals dx, we could use our u substitution. We're going to get du in the numerator, a squared, which is radical 7 squared, plus u squared. We know that this right here gives us the form of arctangent. We're going to get 1 over a, 1 over rad 7, arctangent of u over rad 7 plus c. We're going to substitute our u back in, and once we substitute our u back in, we'll get our final solution. So our final solution is 1 over radical 7, arctangent of x plus 4 over radical 7 plus c. And if you got that, excellent work. Let's try another one. In this case, this is a little bit tricky, but remember, we're going to follow our number one rule of calculus, and that is, if we can simplify first, and then we're going to go ahead and try to apply our rules of calculus. And in this case, what we could do is we could factor out an x squared from the radical. So if you factor out the x squared from x squared minus x to the 4th, we're left with radical x squared times the quantity of 1 minus x squared. Of course, square root of x squared just gives us x, and the x in the numerator and the x in the denominator will cancel. That will give us 2 dx over radical 1 minus x squared. We're going to let u equal x. du then is, of course, dx. We could take that 2 and factor it out, and we get du over radical 1 squared minus u squared. And of course, this is the form of arcsine. So we're going to get 2 arcsine of u over 1 plus c. U, of course, is x. Over 1 is still x. And so we get 2 arcsine of x plus c. And if you were able to do that on your own, good job. Sometimes we need to use some identities in order to solve certain integrals. So let's say, for example, I want to integrate the antiderivative of 1 plus tangent squared of 2x over tangent of 2x plus 2. What everyone should recognize is 1 plus tangent squared is an identity. It's actually secant squared 2x. Now, once we have that, we're going to let our denominator, tangent of 2x plus 2, equal u. du in this case equals 2 secant squared 2x dx. That's appropriate because in the numerator we have secant squared 2x dx. We need the 2. So we're going to multiply it by 2, but if we multiply it by 2, once again, we've changed our problem, and we're going to have to divide by 2. So we end up with 1/2 the antiderivative of 2 secant squared 2x dx all over tangent of 2x plus 2. So now we're going to get 1/2 du over u, and of course this is an ln, so we get 1/2 ln of absolute value of u plus c. We're just going to substitute our u back in, and if you do that, we get 1/2 ln of the absolute value of tangent of 2x plus 2 plus c. Let's try another one. We have quite a difficult next problem. In this case, we want the antiderivative of the quantity of cosecant of 2 theta minus cotangent of 2 theta squared d theta. In this case, I'm going to go ahead and FOIL it all out. We get cosecant squared 2 theta minus 2 cosecant 2 theta cotangent 2 theta plus cotangent squared 2 theta d theta. In this case, we're going to use the identity that cotangent squared 2 theta is equal to cosecant squared 2 theta minus 1. That being said, I could replace cotangent squared 2 theta with cosecant squared 2 theta minus 1. If we do that, combine like terms, we'll end up with 2 cosecant squared 2 theta minus 2 cosecant 2 theta cotangent 2 theta minus 1. We can now separate this, and we'll end up with 2 antiderivative of cosecant squared 2 theta d theta minus 2 antiderivative cosecant 2 theta cotangent 2 theta d theta minus the antiderivative d theta. Using a u substitution, we're going to let u equal 2 theta. du is 2 d theta. And if we apply our u substitution to the first two antiderivatives, we'll end up with 1/2 times 2 antiderivative cosecant squared 2 theta times 2 d theta minus 1/2 times 2 times the antiderivative cosecant 2 theta cotangent 2 theta times 2 d theta minus d theta. If we just simplify and use our u substitution, we'll end up with the antiderivative cosecant squared u du minus cosecant u cotangent u du minus d theta. If you antidifferentiate, we get negative cotangent u plus cosecant u minus theta plus c. And then once again, just substituting our u back in, we'll end up with negative cotangent 2 theta plus cosecant 2 theta minus theta plus c. We must be careful in determining the correct rule. Oftentimes it seems we should use one rule, when another times it's another rule that should be applied. When in doubt, just try the rule that you think is going to make the most sense. If it doesn't work, try another rule. Be diligent, don't quit. Sometimes you're going to use some rules, sometimes it's going to seem impossible at times, but with persistence, you'll see that the hard problems are often the most satisfying to solve. Just know that we have quite a few rules that we can use. We now have some anti-trig rules that we can use. We also, of course, have our ln rule, and then we could also use all of our trig identities. So let me give you a couple of keys to solving integrals of rational functions. First, don't try to integrate improper rational functions. Remember, if you have a degree on the top that's greater than degree on the bottom, you're going to want to divide that first and then try to integrate. Either separate the sum of the difference of the numerator over the denominator or use long division to simplify the function. Try the logarithmic rules. The antiderivative dx over x is ln of x. The antiderivative du over u is ln of u plus c. And of course, you could use your inverse trig rules. The antiderivative du over radical a squared minus u squared is arcsine of u over a plus c. The antiderivative du over a squared plus u squared is 1 over a arctangent of u over a plus c. And of course, the last one, the antiderivative du over u radical u squared minus a squared is equal to 1 over a arcsecant of absolute value of u over a plus c.